All right, so we now have seen how the definite integral can be used to find area. Well, when we define the definite integral, the upper limit of integration was given as a constant. Now, a problem that arises sometimes in calculus is when the upper limit of integration is given as a function of x. So a slightly different situation arises. When the upper limit is given as a function of x. Now, this is where the so-called second fundamental theorem of calculus is going to come in, as the title of this part states. So like I was saying in part 1 of this lecture, if the main idea of this course is building up to the fundamental theorem of calculus, and that's the number one thing that you should know, then the second most important thing you should know is probably the second fundamental theorem of calculus. So one of the things that you should recall from earlier when we defined the definite integral from a to b, and we said that this was equal to f of b minus f of a, this integral gave us, first of all, a integer solution, or a real number as a solution. It didn't give us any functions as a solution. But when we add let me not use x here because it will be misleading. I'm going to be using t whenever I use the upper limit as an x. So whenever we have now a variable as our upper limit, what we're going to have as a solution is going to be a function. We're going to have a function as our solution. So let me illustrate that. So we have, again, definite integral as a number, and that was going to be f of x dx. And again, this is a constant, that a, this b is also a constant, and then this f is a function of x. And the other one that I wrote will be, I'll do it in the bottom, the definite integral as a function of x. And what we have here is f of x being equal to the integral from a to x of some function f of t dt. And again, this is still a constant, but now we have f being a function of x, and we have this f being a function of t. So our problem changes. Let's say somebody asked us to evaluate the following definite integral. So it's given to us as f of x is equal to the integral from 0 to x of cosine t dt. Okay, much like last time, it's always good to write our derivative. So the derivative of sine is cosine, the derivative of cosine is negative sine. I will always do this. you should get into the habit of doing this. Okay, so now we have something to work with. So let's say I have to find this antiderivative, and let's say somebody asks us to find this at the point x equals 0, pi over 6, pi over 4, pi over 3, and pi over 2. Now one way of doing this, which is not the way that I'm going to do it, but one way of doing this would be to substitute the given value of x in the upper bound, or the upper limit of integration. So that would be one way of doing this. You could plug in 0 here. Remember that when you do the integral of from 0 to 0, you're going to get 0. Then you put in pi over 6. Then you put in pi over 4. And you do this, 5 times. You'll do this 5 times. So you'll have to find the antiderivative 5 different times and evaluate it 5 different times. So that's one way of doing this. The other way of doing this will be to actually fix x as a constant. So treat the x as a constant. So the other way of doing this is to fix x as a constant and then apply the fundamental theorem of calculus. What do I mean by fix this as a constant? When you fix x as a constant, you're going to treat it as a number. Even though x is not a number, x here is a variable. So it behaves as a variable will behave. It's an independent variable, so it could take any value you want. When you treat it as a number, you're treating it as if it's fixed, as if it were just one number. So that's what we're going to do now. We're going to fix it as if it were one number. So what do we get? Well, we have, again, f of x is equal to the integral from 0 to x of cosine t dt. So if we're fixing x, we're going to treat it as a number, and we're going to integrate as we normally would. So now what is the antiderivative of cosine? The antiderivative of cosine is sine. So we have that this is equal to sine of x, well, not sine of x, sine of t, because we're doing this with respect to t. So this is sine of t evaluated from 0 to x. Okay? And now we apply the fundamental theorem of calculus. So that means that we're going to do f of b minus f of a. Well, what is b? We're treating b as a constant, so b is x. So we're going to do sine of x minus sine of 0. So again, this right here is going to be my f of b. This right here is going to be my f of a by the fundamental theorem. Now, sine of x is just sine of x. And sine of 0 is 0, so what we get here is sine of x. But notice, what is this equal to? This is equal to the antiderivative from 0 to x of cosine of x dt, which was itself equal to f of x. So we have f of x being equal to sine of x. But notice, this is just a regular function now. And now we can actually simply solve by plugging in the values that we have for x. So now we can solve the problem by simply plugging in for x. Plugging in the values of x into capital F. So what do we get? Well, we will be doing f of 0, f of pi over 6. This is the same thing as sine of 0. This is the same thing as sine of pi over 6. f of pi over 4 actually was the one that I said, pi over 4, f of pi over 3, and f of pi over 2. Okay, so again, if you don't remember how to do this, I suggest that you review pre-calc, because this is definitely there's definitely gonna be a question like this on your final exam, where you have to do something like this. And it's always good to practice using the unit circle and the reference triangles. I prefer to use the reference triangles because I don't like to memorize the unit circle, but either way it's fine. It's going to be 0, and then, and this is, you can think of pi as 180 if you're going to use a triangle, so it's going to be 180 divided by 6, and then you can use the triangle to figure out the angle first time, but this is going to be 1/2. You can also memorize the table. There's a table that people like to memorize. I don't recommend memorizing the table, because you could just derive the table using the reference triangles or the unit circle. If you want to memorize the table, you might as well memorize the unit circle. Anyway, that's a rant for another day. Sine of pi over 3, it's going to be radical 3 over 2. And sine of pi over 2 is 1. Another thing that helps is just knowing the sine wave. So you get pi over 2, 1, 0, 0, and 3 pi over 2 being negative 1. So this also helps a lot. Okay, so another name, let me just give you some other piece of information. Another name for these types of functions that are given as integrals, definite integrals at that, is accumulation functions. Accumulation functions. And the reason for that is this. Let's talk again about the sine wave. So the sine wave looks like this, from 0 to 2 pi. The problem that we were dealing with had us go from 0 to 0, which there's no area, because that's just 0. And then we went from 0 to pi over 6. Well, let's say pi over 6 is here. So we're talking about this area here. Just realized that I made my pi over 2 will be here, which will be the max that we did on this problem. Let's say you have now pi over 4, which will be halfway. And then you had pi over 3 somewhere here. So the first one gives us this area. The second one is going to give us this area plus the red one. The third one is going to give us all of this area plus the blue and plus the red one, and so on. So you're accumulating all of these areas as you move along. So that's why it's called an accumulation function. Okay? There's a lot of applications to this as well in mathematics and physics as well. Now, this so-called result is what we're going to go into the second fundamental. It leads us to the second fundamental theorem of calculus. Because notice the following. My answer for this was f of x equals sine of x. So notice my solution was f of x equals sine of x. If I take the derivative of this, we get f prime of x is equal to cosine of x. But the antiderivative that we were looking for, without the limits of integration, was cosine of t dt. The only difference between this and this is just the variable, the x. So this is what's going to lead us to the second fundamental theorem of calculus. Because if you are given a function, you're told to take the derivative of a function that's given as an integral. Like, for example, if you're told to find the derivative of our f of x dx, then this is the same thing as we just showed as the derivative of sine of x, which is equal to the derivative of our original function with respect to t. That's what I just said. It's equal to cosine of t. Cosine of x, not cosine of t, cosine of x. Okay, so notice, what I'm saying here is that if we take the derivative of a function that's given in terms of an integral, what happens is, in general, not always, but in general, the derivative sign and the integral sign will cancel out, and you will just change the variable that's here with the one that's up here. In general, again, it's not always the case. So again, if somebody tells you, okay, find the derivative of, let me call it g, of g of x, right? But capital G of x is given to you as an integral, let's say from 0 to x, of e to the x plus 2, let's say. Keep saying e to the x, e to the t plus 2 dt, then you can expect this to work as you normally would. So what this is going to be equal to is just e to the x plus 2 when you do it, because the integral signs are going to cancel out and you'll just substitute back in. And you could try it out with this problem on your own, and you could check that the solution is actually true. How do you check? You take the antiderivative and then you take the derivative, and you should get back this, but with just the variable swapped. So let me write the theorem. This is definitely something that's on your final exam for the course. There's always a problem like this on the final, so it's important that you know it. So this is the second fundamental theorem of calculus. And it says the following: if f is continuous on an open interval t, I actually, on an open interval I containing the number a, then for every x in the interval, the following is true: the derivative of the integral of a function evaluated at t is equal to f of x. Okay, so notice what happens here. The integral and the derivative signs cancel out, and you substitute the x into the function. Now, when does this not work? When f is not continuous on that interval, this doesn't work. So that's one of the cases when this does not work. So f has to be continuous on the interval, and the interval has to be open. Okay, so that's the so-called second fundamental theorem. So let's do some examples using the second fundamental theorem, and then we'll do one more theorem or two, and then that'll be the end for this section. Yeah, so it's an example. Okay, so let's evaluate the following. We're told to take the derivative with respect to x from 0 to x of t squared plus 1 dt. There's a problem this type of problem, with a radical, is often given on the final, so keep note of that. Now notice that the first thing you should note by the theorem is that our function has to be continuous for it to work. So the first thing you should check is to see if this expression is continuous, because it's our f of x. So is f of x continuous? on the interval that we're given. So the square root is continuous so long as the inside is positive or 0. So long as there are no negative numbers in here, our function is continuous. But notice, we have a t squared in there, which means that any negative numbers that go in for t are going to come out as positive. Okay, because t is being squared, if you put in a negative number like -2, then you're just going to get a positive number. So this is continuous in the whole number line. Okay, if you plug in 0, it's going to get 1, so it works for every single number that you plug in. So this is a good sign. So that means that we can apply the theorem. So by using the second fundamental theorem of calculus, we have the following: d dx due to x of t squared plus 1 dt is equal to square root of x squared plus 1. That's going to be your solution. Okay, it's a straightforward application because it's continuous. You could try to find the antiderivative of this, but you are not going to be able to, at least in this class, because we haven't covered this specific type of problem. So you don't actually have the techniques yet until next lecture to actually solve this type of problems. So, but we can easily apply the second fundamental theorem and see that we get a solution right away. Let's do another one. Okay, so let's find the derivative of f of x is equal to the integral from pi over 2 to x cubed of cosine t dt. Okay, so notice that we have an x cubed in there, and that's okay. It's not gonna be crazy or that crazy. Let's see what happens. So we have, let's see. Sometimes it is useful to use substitutions, so we could use a substitution here. But let's see what happens. So we have f of x equals to pi over 2 to x cubed cosine of t dt. So if we take the derivative of this, which is what we have to do, notice that we have an x cubed here. Before we had an x to the first. So it is useful sometimes to use a substitution for our problem. So let's try to use a substitution for x cubed. So let u be x cubed. That means that du is going to be equal to 3x squared dx. So this is going to become useful in a second. Remember that by the chain rule, if you take the derivative of x, of f, you're going to have the derivative of f with respect to x times the derivative of u with respect to x, because you're using the chain rule. So that's why we have to be a little bit careful, because this x is not as straightforward as before. But now we know what the derivative, we know what the, not dx, du. I want to do this with respect to u. We know what du dx is equal to, believe it or not. Du dx is right here, which is a substitution that I did. If you divide both sides by dx, you have du dx is equal to 3x squared. And we're taking the derivative with respect to u of this. So let me write that here. F of u is equal to the integral from pi over 2 to u of cosine of t dt. Okay, so I'm just trying to make my life a little bit easier in the end of the problem by using this substitution here. The substitution is right up here with x cubed. Okay, so the derivative of f of x, if I use a substitution by the chain rule, is the derivative of f with respect to u times the derivative of u with respect to x. I know what df du is. Df du is going to come from my fu. So this is what I have. So I have the derivative with respect to u of the function f. So what is my function f with respect to u? My function f with respect to u is pi over 2, the integral from pi over 2 to u of cosine of t dt times du dx. So what I did here, I'm taking the derivative of f, which is this function right here, and I'm going to substitute it in with this, with what is equal to. Then I'm going to multiply by du dx, which is up here. And this just means that I'm taking the derivative of this piece. So now, we know by the fundamental theorem that because cosine of t is continuous on that whole interval, by fundamental theorem, the derivative of the integral from pi over 2 to u cosine t dt is just going to be cosine of u. Okay, so it's going to be cosine, and we're going to swap t with a u, times du dx. Okay, it's going to be cosine of u, so this whole piece goes away, times du dx. But I know what du dx is. Du dx is 3x squared, so this is going to be equal to cosine of u. Well, what was u? U was x cubed, so we have to put that in there. So x cubed times 3x squared, which is what du dx was. So we have that our solution is 3x squared cosine of x cubed. Now, you can actually find the integral without using a substitution, but I wanted to show you using this method because it's what we're going to be using in the following section. So this idea of using substitution is going to become very important as we move on. But you could have just easily found the antiderivative of f of x as it was given, which was pi over 2 x cubed cosine of t dt. The same way that I did before, the antiderivative of cosine of t is sine of t from pi over 2 to x cubed. And again, by the fundamental theorem of calculus, the first one, this is sine of x cubed minus sine of pi over 2. Sine of pi over 2 is 1. So we get sine of x cubed minus 1, because sine of pi over 2 is 1. But that's the value of the integral. So we have f of x is equal to sine of x cubed minus 1. But now remember that the problem, I don't expect you to remember at this point, it was to find the derivative of f of x. I now have rewritten f of x. So if you take the derivative, you find f prime of x, the derivative of sine x cubed, the derivative of sine is cosine, so it's going to be cosine of x cubed, but by the chain rule, because remember this is a function on the inside, we have to multiply by the derivative of the inside, which is 3x squared, and the 1 goes away because the derivative of constant is 0, so it's equal to 3x squared cosine of x cubed, which is what we had up here using substitution. Now you may say, well, the substitution that you did was much more confusing and longer, and I will agree with you, but again, I'm motivating the next section because there will be functions that will not be easily integrable directly, for which you will have to use substitutions. Okay, let's talk about one more theorem, and this is called the net change theorem. So There's another theorem that is not in your final, but you will see it in your homework, and you will definitely see it in other courses. So, the fundamental theorem of calc, the first one, fundamental theorem of calculus, states that if f is continuous on the closed interval a, b, then, and this is key, and f is an antiderivative of f on the closed interval AB, then the following is true. So this is what the theorem says. It says that the interval from a to b of little f of x dx is equal to the antiderivative evaluated at b minus the antiderivative evaluated at a. But we know that the following is also true. We know that the derivative of the antiderivative is little f of x, meaning if you take the derivative of the antiderivative, you're going to get back this function right here. Think about it. Let me do a quick example. X cubed dx. If you take the antiderivative of this, well, what is the antiderivative of x cubed dx? Capital F of x is going to be equal to x to the 4 over 4. That's by the rules. And now if you take the derivative again, you're going to get 4x cubed over 4, which is x cubed. So, but x cubed was little f of x, meaning this right here. So that's what I'm saying. Since f prime of x is equal to little f of x, we can write the fundamental theorem as follows. Fundamental theorem as follows. We can write it as the integral from a to b of the derivative of x dx, and that is equal to, again, f of b minus f of a. And this quantity now, this f of b minus f of a, represents the so-called net change of f on the interval AB. Okay, I'm not going to do an example of this. I just wanted to introduce the theorem because these examples are a bit longer. All of them involve word problems, and you honestly will not need them in this class. However, if you do take a physics class, especially physics with calc, because at Lehman we have two physics courses. We have physics for with an algebra point of view and physics with a calc point of view. If you take the physics with calc, this theorem is going to be very helpful to you. For those of you who will be majoring in physics or minoring in physics, this is something that you should definitely know. And again, thank you for your time, and that is the end of this lecture. You should definitely, again, go over both of the fundamental theorems as they are very important.